All right, so we are going to do the first problem from the review, and that is we want to calculate the integral from 2 to infinity, and I just updated this on Canvas because I originally made a mistake. It's asking a question, so it's not a mistake, but I had a 0 here, which makes the problem a lot harder. So now we want to integrate what? 1 over e to the power of y squared minus 4y plus 4 over 2. And we're integrating this with respect to y. So I said in the kind of lead up to this problem that what we're going to want to do is we want to compare the inside of this integral to the PDF of a normal random variable. So we really want to compare this to the PDF, so the probability density function of a normal random variable. And what we're going to want to do is we're going to want to make this inside look like a PDF of a normal random variable. First by kind of manipulating the expression a little bit, and then by multiplying and dividing by the right constants to make it equal to a PDF. So if we have a random variable x that is normal with mean mu and standard deviation sigma, then this random variable has a probability density function f of x, which is equal to 1 over sigma times the square root of 2 pi times e to the minus x minus mu squared over 2 sigma squared. So this is the PDF that we kind of want to make this look like. So the first thing we want to note is that this e is in the denominator, right? And here we have the e in the numerator and a negative sign in front of this. So we really want to bring this e to the top. And when we do that, we need to multiply. We need to change the sign to make it negative, right? So the first step, like I just said, now we want to integrate from 2 to infinity. We bring this to the top. When we do that, we have a minus now, y squared minus 4y plus 4, and this is over 2 still, and we're integrating with respect to y. So now what we want to do, you can see when you compare these two, right, this is a minus x minus mu squared, and in here we have this quadratic expression. So what we really want to do is, in general, what we would need to do is complete the square. But if you notice, I take half of this, it's -2, I square it, I get 4. So actually, this is already a square. So let's confirm that over to the side. So we have y squared minus 4y plus 4. So if we factor this, what are we going to get? We're going to get y minus 2 is equal. So this is equal to y minus 2 squared. So now the right expression. So this is equal to the integral from 2 to infinity of e to the minus y minus 2 squared over 2 dy. So now it's starting to look a little bit like a normal probability density function with a mean of 2. I mean, this looks very similar, except for my mu is going to be 2, my y is x. And now if I compare the denominator, of this exponent, This is 2. This is 2 sigma squared. So I really want what? I really want sigma squared to be equal to 1. If I do that, then this will be in the form that I need, right? So if sigma squared is equal to 1, I have all that sigma is equal to 1. Square root of 1 is 1. So now I really need to add this expression here. I need to add this expression 1 over sigma times the square root of 2 pi. And in my case, in this case, our case, sigma is equal to 1. So what do I need to do? I need to add this square root of 2 pi in the denominator. But I can't just divide by square root of 2 pi. That's going to change the expression. So I also need to multiply by the square root of 2 pi. So I'm basically just cleverly multiplying by 1. And then this is times e to the minus y minus 2 squared over 2. This is dy. And now let's pull this out, because I want this to be looking like the probability density function of a normal random variable. So to do that, I need to pull this square root of 2 pi out. So now this is square root of 2 pi times the integral from 2 to infinity times 1 over the square root of 2 pi times e to the minus y minus 2 squared over 2 dy. So now when we look at the inside of this, this is exactly the PDF, the probability density function of a normal random variable with mu, which is equal to the mean, equal to 2, and the standard deviation, which is equal to sigma, equal to 1. You can just plug this 2 in for mu up here and 1 in for the standard deviation. And then if you change the variable to y, you'll get exactly this expression. So now if we had that we were integrating from negative infinity to infinity, this integral would be exactly equal to 1, right? So let's get this up. Sorry about that. Right. But we do not have that. That is not the case, right? We're integrating instead from 2 to infinity. So what do we want to do? We need to use the symmetry. We need to use the symmetry of a normal random variable density function. So for a normal random variable, the density function looks like this. Right? So right in the middle is going to be my mean, mu. So if I'm integrating from negative infinity to infinity, that's the area under the curve here. That's going to be exactly equal to 1. So because of the symmetry of this graph, my mu is now equal to 2. So now I'm saying if I integrate from 2 to infinity, it's going to be this. It's going to be exactly a half of my total area under the curve, which is the total area under the curve is going to be 1. So this area inside of here is going to be exactly 1/2. So now what do I have? I have that this is equal to the square root of 2 pi times 1/2. So this is equal to square root of 2 pi over 2. So I really enjoy this method. I think it's a little confusing when you first see it, but it's really nice because you don't actually have to integrate. That is what I like most about it. So sorry that I didn't move the camera down, so maybe you didn't see all this while I was doing it, but I moved it up. I moved it down eventually, so hopefully you could fast forward and then rewind to think about whatever, it's fine. Let me know if you have questions, and that is it for the first video.